Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at E and Z and Cis and Trans isomerism. We're going to talk about what E and Z isomerism is, what Cis and Trans isomerism is, and why alkenes can have stereoisomers. And we're going to look at the naming of E and Z isomers using CIP Priority Rules. Alkenes and their reactions have been covered in separate videos. Check the links in the description below. Before we talk in detail about E and Z and Cis and Trans isomerism, there are a few essential ideas you need to be comfortable with. Alkenes are unsaturated hydrocarbons that have a carbon-carbon double bond in their carbon chain. The carbon-carbon double bond is made up of a sigma bond and pi bond, with the pi bond being unable to rotate, giving alkenes restricted rotation. The bonds to each carbon in the double bond are in the same plane, giving a trigonal planar and flat arrangement of bonds, almost like a piece of paper. Isomers are molecules that have the same molecular formula but a different structure or spatial arrangement of atoms. Basically, they contain the exact same atoms, but they aren't the same molecule. Stereoisomers are isomers that show a special type of isomerism, where molecules have the same structural formula but a different arrangement of atoms in space. A bit like your hands have the same types of fingers in the same order next to each other, but your left hand and right hands are still different. Recap done? Let's go! As the carbon-carbon double bond in an alkene has restricted rotation and is unable to rotate, atoms or groups bonded to it are fixed in their positions. For example, if two atoms were bonded to an atom that is single bonded to another atom, those two atoms can swap places of each other in space as the other single bond is rotated. If the same two atoms were bonded to a carbon that is double bonded to another carbon, however, these two atoms are no longer able to swap places of each other as the carbon-carbon double bond is unable to rotate. The only way these two atoms could swap positions in space is if the whole molecule is rotated and turned upside down. The problem with this is that the atoms or groups bonded to the other carbon from the carbon double bond will also have to get flipped. If this other carbon from the double bond is bonded to two groups that are the same, this flipping upside down doesn't matter at all, as even when flipped, the same groups are occupying the same positions as before. However, if the other carbon is bonded to two different atoms or groups, as the molecule gets flipped upside down, the arrangement of these two groups in space changes. This means that the four atoms or groups bonded to a double bond are fixed into place relative to each other. No problem if they are all the same, but if they are different, there are two different ways these groups can be arranged, giving two isomers. These are stereoisomers as they have the same structural formula, but in space the atoms are arranged differently. For example, in 1-bromo-2-chloroethene, carbon 1 has a bromine group bonded to it and carbon 2 has a chlorine bonded to it. There are two possible ways that the bromine and chlorine could be arranged around the double bond, relative to each other. This gives two isomers. This can create a real headache when naming molecules that show this type of isomerism. From our example, we now know that the name 1-bromo-2-chloroethene refers to two different possible molecules. We need to be able to specifically refer to each isomer when using a name. To help, we use a system called E and Z notation, with one isomer being called the Z isomer and the other the E isomer. To give E and Z names, it is first essential to determine which atom or group we are going to use on each carbon as a reference point. To do this, we assign a priority. CIP or Cahn-Ingold pre-log rules are followed. Basically, we look at the two groups bonded to each carbon and decide which one is more important in order to help us name the isomer. The highest priority group is normally the one that has the highest atomic number. For example, if you have a chlorine and bromine group bonded to the same carbon, the bromine has a greater atomic number and will be considered the higher priority. If this isn't possible and the two atoms bonded have the same atomic number, for example 2 carbon groups, then you look at what those atoms are bonded to themselves and compare their atomic numbers. For example, if you have a CH3 and a CH2CH3 group bonded to the same carbon, the CH2CH3 group will be given the highest priority, as here the carbon is bonded to another carbon, whereas the carbon in the CH3 group is only bonded to hydrogens. Once each highest priority group is assigned on each carbon, we can now compare their orientation to each other. If both groups are on the same side of the double bond, we call it a Z isomer. Z comes from the German word for together. I personally remember it as Z for same, as in same or same side, but whatever works for you. If, however, both groups are on opposite sides of the double bond, we call it an E isomer. E comes from the German for opposite. If you remember Z for same, then you know E must be opposite, as there are only 2 possibilities. So you don't need to waste time learning 2 ways of remembering it. For example, if we look at 2-chloro-but-2-ene, we can see there are 2 possible ways of drawing the molecule. To name these as either Z or E, we first need to assign the highest priority group on each double bonded carbon. On carbon 2, we have a chloro Cl group and a methyl CH3 group. The Cl has a higher atomic number than the carbon, meaning it is the highest priority group. On carbon 3, we have another methyl CH3 group and a hydrogen group. The carbon has a higher atomic number than hydrogen, meaning this CH3 group is the highest priority. In the first molecule, the highest priority groups on each carbon are on the same side of the double bond. This means this configuration is the Z isomer. Remember, Z for same side. The full name of this molecule is Z2-chloro-but-2-ene. In the second molecule, the highest priority groups on each carbon are on opposite sides of the double bond. This means an E configuration isomer. The full name of this molecule is E2-chloro-but-2-ene. Now we can specifically refer to either stereoisomer by name. This is really important when dealing with organic reactions, especially during drug manufacturing, where it is essential you have the correct stereoisomer, as one stereoisomer may lead to a safe product and the other may lead to a toxic product. When 2 of the groups bonded to both carbons in the double bond are the same, we can make life a little bit easier for ourselves by using cis and trans notation. These isomers are sometimes referred to as geometric isomers. For example, in but-2-ene, the double bonded carbons are each bonded to a methyl CH3 group and a hydrogen. If the identical atoms or groups are on the same side of the double bond, this would be considered a cis isomer. If they are on opposite sides, it would be a trans isomer. In the first molecule here, both the CH3 groups and hydrogen atoms on each carbon are on the same side of the double bond, making it the cis isomer, cis-but-2-ene. One way of remembering this is that you can make a C shape, C for cis, with the bonds going from the same groups to the double bond. In the second molecule, the CH3 groups and hydrogen atoms on each carbon are on opposite sides of the double bond, making it the trans isomer, trans-but-2-ene. You may have spotted here that cis isomers seem to have a Z stereoisomer configuration and trans isomers an E stereoisomer configuration. This is nearly always true, but there are some exceptions, although it is unlikely you will come across too many at this level. The problem is that cis and trans naming doesn't always work when naming more complicated stereoisomers. Z and E naming, however, will always work. At this level, all you need to remember is that for there to be cis and trans isomerism, 2 groups bonded to each carbon from the double bond have to be the same. For Z and E isomers, all groups can be different. As confusing as it may seem, cis and trans isn't the same as Z and E, so treat them separately. So, to To summarize, the carbon-carbon double bond in an alkene has restricted rotation, meaning groups bonded to each carbon can be in one of the two positions relative to each other and they can't move. This can lead to stereoisomerism when the two groups bonded to each carbon are different. E and Z notation is used to name the two stereoisomers of an alkene. Z isomers have the highest priority group bonded to each carbon from the double bond on the same side of the double bond, and E isomers have the highest priority groups on opposite sides. Cahn-Ingold-Prelog, or CIP Priority Rules, are used to assign the highest priority groups on each carbon. The highest priority group is the one that has the highest atomic number. If the two bonded atoms have the same atomic number, for example they are both carbon, then you look at what those atoms are themselves bonded to. For example, a CH2Cl group would have a higher priority than a CH3 group. If one of the two groups bonded to each carbon in a double bond are the same, Cis and Trans is used to name the isomers. These isomers are sometimes referred to as geometric isomers. In cis isomers, both groups are on the same side of the double bond, whereas in trans isomers, they are on opposite sides. It is really important to remember that cis and trans isomerism only applies to alkenes where one of the two groups bonded to each carbon from the double bond are the same. If they are different, E and Z notation must be used. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.